In order to calculate the electromotive force of a cell, we must use the standard electrode potentials of each of the half cells. We know that the half cell on the left of the double parallel line will represent the oxidation, and the half cell on the right of the double parallel line will represent the reduction. Knowing each of the half cell electrode potential values, we can calculate the electromotive force by subtracting the electrode potential of the cell in the cathode minus the electrode potential of the same in the anode. We also know that by convention, we write the more positive value on the right side, which represents the reduction, and the more negative side on the left side. So we can express the electromotive cell value as the electrode potential on the right-hand side minus the electrode potential on the left-hand side. When we studied thermochemistry, we saw that we can tell if a reaction would be spontaneous or not based on the free Gibbs energy and the entropy values. In the case of the redox reactions, we can use the electrode potential values of a cell to predict if a reaction would be spontaneous or not. If the electromotive force of the cell value is positive, then the reaction would be spontaneous. Let's analyze the reaction above and decide if the reaction is spontaneous or not. The cell for magnesium has a more negative value than the one for copper, so the magnesium would be oxidating and the copper will be reducing. That means that the magnesium will be the anode and the copper will be the cathode. In this case, the value of the cathode is 0.34 positive and the anode value is negative 2.37 volts. The electromotive force for this cell would be then 2.71 positive, which we can tell that is a positive cell value, and then it corresponds to a spontaneous reaction. In this second example, we have to determine if the reaction of zinc with iron ions would be spontaneous or not. We see that the value for the electromotive force in the first half equation is more negative, and that means that the zinc will be oxidating and the iron will be reduced. So if we calculate the electromotive force for the reactions, it would be minus 0.44 minus the negative value of 0.76, which gives a total value of 0.32 positive, and that means that the zinc will react with iron 2 plus ions to produce metallic iron and zinc ions. The most powerful reducing agents will be found at the most negative end of the series on the right. For example, lithium metal is a very strong reducing agent. Please notice that lithium is on the right of the equation, so it will oxidize, forcing the other species to reduce. On the other hand, the most powerful oxidating agents will be found at the most positive end of the series on the left. For example, fluorine is the strongest oxidating agent. Please notice that fluorine is on the left of the equation, so it will reduce, forcing the other species to oxidize. If we need to calculate the electromotive force for this reaction, so lithium will react with fluorine to form lithium fluoride, and the electropotential value will be 2.87 minus negative 3.03, which would be a total value of 5.9 volts. Remember that when we were studying thermochemistry, we used to multiply the enthalpy values depending on how many moles we have in the reaction for the Hess law or something like that. The electromotive force is not an extensive property, so we do not need to multiply anything. Just use the values of the electrons potentials as they appear in the table, even though the amount of electrons interchanged are different. What I mean is, even though to balance the redox equation in the sample, you need to multiply the half equation for fluorine by 2, the electropotential value stays the same. More positive minus less positive. That's it. In this new example, we need to determine if hydrogen reacts with a mixture of iron 2 and iron 3 ions. We have 3 equations. The question is asking us about bubbling hydrogen, so hydrogen should appear on the left of the equation. That means that the second equation must be flipped, and we cannot use the third equation because it's negative. In other words, if we choose the second and third equation, the iron would be reacting with protons to produce iron 2 ions because we need to flip the third equation. If we use the first one and the second one, the less positive is the one for hydrogen, and that is the one that we must flip. Now we can calculate the electropotential difference between both reactions. Since the iron 3 reduction potential is more positive, we need to flip their reaction in hydrogen, and their electromotive force for that cell would be 0.77 volts minus 0. The electromotive force is positive, so the hydrogen will reduce the iron 3 ions into iron 2 ions, producing protons in the solution in a spontaneous reaction. For a metal ion metal half cell, if the concentration of aqueous ions in solution increases, the value of the electropotential becomes more positive. This happens because the ions are more likely to be reduced if there are more of them in a given volume of the solution. In the contrary, for a metal ion metal half cell, if the concentration of aqueous ions in solution decreases, the value of the electropotential becomes less positive or also decreases. This happens because the less ions are less likely to be reduced if there are less of them in a given volume of the solution. On the picture on the left, we have both concentration of ions being 1 molar, and we can calculate the value of the electrochemical cell as 1.1 volts because the copper half cell value is 0.34 and the value of the zinc is negative 0.76. So adding those values, we will obtain 1.1 volts. The actual value for the half cell on the copper, when we decrease the concentration to 0.01 molar, which is represented in the picture on the right, will make the electromotive force for the cell to have a total of 1.047 because the copper electrode will reduce the value to 0.287 instead of 0.34. Let's analyze this situation using Le Chatelier principle. Look at the half equation for copper on the right. If we decrease the copper concentration in the solution, the ions, the equilibrium for that cell will shift to the right, taking out some of the electrons as well. Those electrons that come from the zinc area and were used to reduce the copper ions to copper will now accumulate in the copper electrode, reducing the electron potential and make it less positive. The difference between both cells then would be smaller. In this example, we increase the concentration of zinc ions to 2.0 molar instead of 1 molar. So on the right, you see that the electropotential decreases. That is because increasing the concentration of zinc ions will increase the value of the electropotential for zinc. That was negative, so it's going to be less negative or more positive. That's why the difference in between the two half cells are going to be smaller. Let's use the Chatelier principle to analyze this situation as well. Look at the half equation for zinc now. If we increase the concentration of zinc ions in the solution, the equilibrium for that cell will shift to the left, producing less electrons in the zinc electrode. Those electrons missing will change the electrode potential, making it more positive. The difference between both cells then would be smaller. We saw how the concentration of the ions in solution can modify the value of the electromotive force for an electrochemical cell. The size of the solid electrodes does not change the value, since we cannot talk about concentration when we talk about solids.